Section 1 Introduction. In this paper, we aim to enhance the capabilities of text-to-image diffusion models that are currently used for generating images from text descriptions. While these models have demonstrated remarkable performance, they still face difficulties when it comes to generating images with specific and detailed attributes from textual guidance. We have identified two key tasks in the text-to-image generation domain that we wish to address. 1. Subject-driven generation. This task involves generating images of the same subject but in different contexts using a few existing images and the guidance of a text prompt. 2. Controllable generation. This task requires us to generate images from a text prompt and an additional control signal such as edge outlines or segmentation maps. To accomplish these tasks without compromising the original generative abilities of the pre-trained models, we need to implement fine-tuning strategies effectively. An ideal fine-tuning method should balance efficient training with fewer adjustable parameters and fewer training epochs, while maintaining the high quality and diverse generative performance of the pre-trained model. Current fine-tuning approaches either slightly adjust the existing weights of the neurons or add a small component with redefined neuron weights. However, these methods don't guarantee the preservation of the pre-training generative performance. This is partly due to the lack of a proper measurement for quantifying the preservation of pre-trained generative ability. Currently, it's assumed that a smaller Euclidean distance, straight line distance in a multidimensional space, between the fine-tuned and pre-trained models means better preservation of the pre-training abilities. But we argue that the Euclidean difference alone isn't enough to fully capture the degree of preservation of semantic information, hence a more structural measure is needed. To address this issue, we propose the use of hyper-spherical energy, a concept inspired by how well hyper-spherical similarity can encode semantic information. Hyper-spherical energy refers to the sum of the hyper-spherical similarities, like cosine similarity, between all pairs of neurons within a layer, indicating how uniformly the neurons are distributed on the hypersphere. We hypothesize that a good fine-tuned model should have minimal difference in hyper-spherical energy compared to the pre-trained model. This led us to propose orthogonal fine-tuning, OFT, a method which applies an orthogonal transformation, a transformation that preserves the angle between any two vectors, to all neurons. This way, we can adapt large text-to-image diffusion models to a downstream task without altering its hyperspherical energy. To give an intuitive understanding of why an orthogonal transformation works, we can refer to the 2D Fourier transform in image processing. In this context, the angular information, phase spectrum, between input and basis is crucial in preserving the major part of semantics of the image. This suggests that altering the neuron directions is key to modifying the generated image semantically, which is the goal of both subject-driven and controllable generation tasks. However, altering neuron directions extensively can negatively affect the pre-training generative performance. To address this, we propose preserving the angle between any pair of neurons, following the assumption that these angles are crucial for representing the knowledge of neural networks. Our OFT approach is also influenced by orthogonal over parameterized training, a method used to train classification neural networks from scratch. This method keeps the hyperspherical energy small during training, which leads to better generalization in classification. However, there are key differences. For instance, our method seeks to keep the hyperspherical energy the same as the pre-trained model, rather than minimizing it, to ensure that the pre-trained structure isn't destroyed by fine-tuning. We also propose a variant of OFT, constrained orthogonal fine-tuning, COFT, which constrains the fine-tuned model within a certain radius of the hypersphere centered on the pre-trained neurons, keeping the Euclidean distance between the fine-tuned model and the pre-trained model small. Our contributions can be summarized as follows. 1. We introduce a new fine-tuning method, orthogonal fine-tuning, for enhancing text-to-image diffusion models and a constrained variant to improve stability. 2. Unlike existing methods, our approach preserves the hyperspherical energy during model fine-tuning, which we found to be an essential measure for maintaining the semantic generative abilities of the pre-trained model. 3. We apply our methods to subject-driven and controllable generation tasks, showing substantial improvements over previous methods in generation quality, convergence speed, and fine-tuning stability. Additionally, our method converges well with fewer training images and epochs. 4. For controllable generation, we introduce a new metric to evaluate controllability, which involves estimating the control signal from the generated image and then comparing it with the original control signal. This validates the strong controllability of our proposed method. Section summary. The paper proposes a novel fine-tuning method called orthogonal fine-tuning, OFT, for text-to-image diffusion models to achieve better controllability without losing pre-training generative performance. OFT preserves the hyperspherical energy of the pre-trained model by learning a layer-shared orthogonal transformation for neurons. A constrained variant, constrained orthogonal fine-tuning, COFT, is also proposed to limit the angular deviation from the pre-trained model. COFT is shown to significantly improve generation quality, convergence speed, and fine-tuning stability in subject-driven and controllable generation tasks. A new control consistency metric is introduced to evaluate controllability. Section 2. Related work. Our discussion begins with reviewing previous work in related fields. The first category of work revolves around text-to-image diffusion models. We've seen a considerable advancement in text-to-image generation recently, largely attributed to the rapid evolution of diffusion-based generative models and the learning of vision language representation. Models like Glide and Imagine use a diffusion-based approach in pixel space. Glide combines the training of a text encoder with a diffusion prior using paired text-image data, whereas Imagine utilizes a previously trained and frozen text encoder. Models like Stable Diffusion and DAL-E2 operate in the latent space. Stable Diffusion employs VQ-GAN to learn a visual codebook for its latent space, whereas DAL-E2 utilizes CLIP to construct a joint latent embedding space for representing both images and text. Apart from diffusion models, text-to-image generation has been explored using generative adversarial networks and autoregressive models. COFT is an inherently model-agnostic fine-tuning method that can be applied to any text-to-image diffusion model. The second category concerns subject-driven generation, which takes into account a user-provided mask to prevent subject modification. Methods like inversion can be used to modify the context without altering the subject. Some approaches can perform both local and global editing without the need for input masks, but these often struggle to preserve identity-related details. In a method called pivotal tuning, a generator is fine-tuned around an initial inverted latent code with added regularization to conserve the identity. There are also methods that learn a personalized generative face prior from a person's face images. While these can generate different variations of an instance, they may lose specific details. A technique called Dream Booth fine-tunes the text-to-image diffusion model using a reconstruction loss and a class-specific prior preservation loss, leveraging a custom token and a few subject images. COFT utilizes the Dream Booth framework, but rather than basic fine-tuning with a small learning rate, it uses orthogonal transformations. The third category is controllable generation. The task of image-to-image translation can be seen as a type of controllable generation, and most earlier methods have predominantly used conditional generative adversarial networks. Diffusion models have also been used for this task. More recently, ControlNet has shown impressive controllable generation performance by adapting a pre-trained diffusion model to additional control signals through fine-tuning. Similarly, T2I Adapter fine-tunes a pre-trained diffusion model to gain better controllability over the generated images. In our study, we use COFT to fine-tune pre-trained diffusion models, resulting in consistently better control with fewer training data and fewer fine-tuning parameters. Importantly, COFT does not introduce any additional computational burden during test time inference. Finally, we have model fine-tuning. As a type of fine-tuning, adaptation methods are extensively researched in natural language processing. LoRa is a notable related work to COFT, as it assumes a low rank structure for the additive weight update during fine-tuning. Conversely, COFT uses a layer-shared orthogonal transformation to update neuron weights in a multiplicative manner. This method preserves the pairwise angles among neurons in the same layer, leading to improved stability. Section Summary. The section discusses various approaches to text-to-image generation, including diffusion models, subject-driven generation, and controllable generation. COFT is a model-agnostic fine-tuning approach that can be applied to any text-to-image diffusion model, and it uses layer-shared orthogonal transformation to update neuron weights in a multiplicative manner, which yields better stability. COFT also achieves better controllability with fewer training data and less fine-tuning parameters, without introducing any additional computational overhead during test time inference. Section 3. Orthogonal fine-tuning. In Section 3, we discuss the concept of orthogonal fine-tuning. We start by exploring why orthogonal transformation is an effective strategy when fine-tuning text-to-image diffusion models. We break down this discussion into two smaller inquiries. 1. Why it's beneficial to fine-tune the directions, or angles, of neurons, and 2. Why we choose to use orthogonal transformation to accomplish this. To answer the first question, we look to observational evidence that suggests differences in angular features of neurons correlate strongly with semantic gaps, or differences in meaning. It's been demonstrated by SphereNet that when we train a neural network with all neurons normalized onto a hypothetical unit sphere, the network exhibits similar capacity and potentially even superior generalizability. This suggests that the direction of neurons is key in capturing crucial information from data. To further illustrate the significance of neuron directions, we run a small-scale experiment in which we train a standard convolutional autoencoder using a set of flower images. During training, we use the standard inner product to generate the feature map, where Z represents the output from the convolution kernel W in relation to the input X from the sliding window. During testing, we compare three methods to generate the feature map: A, the inner product used in training; B, magnitude information; and C, angular information. Our findings suggest that the angular information of neurons can almost flawlessly reconstruct the input images, whereas the magnitude information offers no substantial utility. It's worth noting that we didn't use the cosine activation, method C, during training. Our training relied solely on the inner product. This suggests that the directions of neurons are primarily responsible for retaining the semantic information of input images. Therefore, to alter the semantic information of images, it's likely more effective to fine-tune the directions of the neurons. For the second question, the simplest method to adjust the direction of neurons is to rotate or reflect all the neurons in the same layer simultaneously, which naturally involves an orthogonal transformation. While it might be more flexible to use another angular transformation that rotates different neurons at different angles, we find that orthogonal transformation offers a good balance between flexibility and regularity. Furthermore, previous research has shown that orthogonal transformation is sufficiently powerful for training neural networks. To back up our argument, we conduct an experiment to demonstrate the effective regularization induced by the orthogonality constraint. We perform the controlled generation experiment following the setup of ControlNet, and present our results in a following figure. We note that our standard orthogonal fine-tuning performs quite steadily and achieves precise control after the training concludes, by epoch 20. In contrast, an approach without the orthogonality constraint fails to generate realistic images and achieves no control effect. This experiment underscores the importance of orthogonality in orthogonal fine-tuning. Section summary. The authors discuss the benefits of using orthogonal transformation in fine-tuning text-to-image diffusion models. They argue that the direction of neurons plays a major role in storing semantic information, and that fine-tuning neuron directions is likely more effective in modifying the semantic information of images. They also demonstrate the effective regularization induced by the orthogonality constraint through a controllable generation experiment. Section 3.2 General Framework. In Section 3.2, we discuss the general framework for fine-tuning models. The typical approach to this process involves utilizing gradient descent along with a small learning rate to adjust a model, or certain layers within the model. This small learning rate implicitly encourages minimal divergence from the original, pre-trained model. Essentially, the aim of standard fine-tuning is to continue training the model while keeping the differences between the adjusted model's weights, we'll call this M, and the original model's weights, we'll call this M0, to a minimum. However, while this approach makes intuitive sense, it might not always be the best choice for large models. That's where LoRa and OFT come in, as they introduce additional constraints during the weight update. LoRa introduces a low-rank constraint, essentially stating that the difference in rank, a measure of matrix dimension, between the fine-tuned and pre-trained model is some small number, let's call it R. OFT, on the other hand, uses a constraint for the similarity between each pair of neurons in the model. It essentially requires that the hyper-spherical energy, a type of measurement used in high-dimensional spaces, of the model's weight matrix remains the same before and after fine-tuning. Consider a fully connected layer of neurons in our model, with weights we'll denote as W. We'll call each neuron within this layer W_I and the pre-trained weights as W0. The output vector, Z, of this fully connected layer is computed by multiplying the transpose of the weights with the input vector, X. In the case of OFT, this approach can be interpreted as trying to minimize the difference in hyperspherical energy between the fine-tuned model and the pre-trained model. To put it simply, we're comparing the energy of each normalized neuron in the fine-tuned model with its equivalent in the pre-trained model. We'll achieve the minimum difference, which is 0, if the fine-tuned and pre-trained model only differ by a rotation or reflection. This is the basic idea of OFT. We fine-tune the neural network by learning orthogonal matrices whose transpose equals its inverse, to transform neurons in each layer. Formally, in OFT, we optimize an orthogonal matrix, R, for a pre-trained fully connected layer with weights W0. This changes the computation of the output vector from being based solely on the pre-trained weights to include the orthogonal transformation, i.e., Z becomes equal to the product of the transpose of the product of R and W0 and the input vector X. Here, R is constrained to be orthogonal, its transpose equals its inverse, and the weight matrix, W, represents the fine-tuned weights. To begin the fine-tuning process with OFT, we start from the pre-trained weights, which is achieved by Initializing the orthogonal matrix R as an identity matrix. We use differential orthogonalization strategies to ensure R remains orthogonal. In the following sections, we'll discuss how to maintain orthogonality in a computationally efficient manner. Section Summary. The conventional fine-tuning strategy updates a model with a small learning rate to minimize the difference between the fine-tuned and pre-trained model weights. However, this can be too flexible for large models. LoRa introduces a low-rank constraint, while OFT introduces a constraint for pairwise neuron similarity by optimizing an orthogonal matrix to transform neurons in each layer. OFT ensures fine-tuning from the pre-trained model by initializing the orthogonal matrix to be an identity. Matrix. Section 3.3 Efficient Orthogonal Parameterization. In Section 3.3, we discuss an effective way to parameterize orthogonality. Common methods such as the Gram-Schmidt process, though they're differentiable, are often too costly to use in practical settings. To get around this, we use what's known as Cayley parameterization to create our orthogonal matrix. The process involves the creation of an orthogonal matrix, denoted as R, using an equation that combines a skew-symmetric matrix, Q, which is the negative of its own transpose, with the identity matrix, I. Here's how it works in plain terms. We add Q to the identity matrix, then multiply this result by the inverse of the result of subtracting Q from the identity matrix. However, the Cayley parameterization comes with a small drawback. It can only generate orthogonal matrices with a determinant of 1. These matrices belong to a specific group known as the special orthogonal group. The good news is, this limitation doesn't hamper our performance in actual use. Now, even with the Cayley transform, parameterizing the orthogonal matrix R can still be quite inefficient, especially when dealing with large dimensions. So, we propose a solution. We'll represent R as a block diagonal matrix, broken down into R blocks. This R matrix is essentially a matrix containing smaller orthogonal matrices along its diagonal. When R is equal to 1, this matrix just becomes a standard unconstrained one. The number of parameters in an orthogonal matrix of size d by d is half of the product of d and d1, leading to a complexity of d squared. However, if we represent this matrix as an R block diagonal orthogonal matrix, the number of parameters becomes half of the product of d and d r 1 foot, which results in a complexity of d squared divided by r. We can further reduce the number of parameters by sharing the block matrix, which means all the R blocks in our matrix are identical. This strategy brings down the parameter complexity to d squared divided by r squared. It's worth noting that no matter how we optimize parameter efficiency, our R matrix still maintains its orthogonality, preserving what's known as hyper-spherical energy. Now, let's compare our orthogonal Fourier transform, OFT, with the low-rank adaptation, LoRa, in terms of parameter efficiency. LoRa, with its low-rank parameter denoted as R', has a number of trainable parameters equal to the product of R', D, and N. Assuming both R and R' depend on the neuron dimension, D, then the parameter complexity of LoRa becomes D squared plus D times N, while the parameter complexity of OFT becomes D. For instance, consider a weight matrix of size 128 by 128. LoRa would have 2048 trainable parameters with R' equals to 8, while OFT would only have 960 trainable parameters with R equals to 8, assuming no block sharing. Thus, OFT generally shows better or comparable parameter efficiency than LoRa. Section Summary. The authors propose an efficient method for generating orthogonal matrices using Cayley parameterization, which can produce matrices with determinant 1 belonging to the special orthogonal group. To further improve parameter efficiency, they suggest representing the orthogonal matrix with a block diagonal matrix with R blocks, which reduces the parameter complexity to O, D squared, R squared. This method is compared to LoRa and found to be more parameter efficient in most cases. Section 3.4 Constrained Orthogonal Fine-Tuning. In Section 3.4, we talk about an approach that we call Constrained Orthogonal Fine-Tuning, COFT. This is a way to further refine the original orthogonal fine-tuning, OFT, technique by limiting the alterations of the fine-tuned model such that it stays close to the original pre-trained model. What does this look like in practice? Well, during the forward pass of our model, we multiply the input, represented by X, by a certain matrix, W, which has been further modified by another matrix, R. This process ensures that R maintains a relationship with itself such that when we multiply R by its own transpose, we get the identity matrix, often denoted as I. Additionally, we also ensure that the difference between R and the identity matrix I is within a certain threshold, denoted by epsilon. This way, we're imposing two constraints, one of orthogonality and another one of deviation from the identity matrix. Achieving the orthogonality can be managed by using a technique we introduced earlier, called the Cayley parameterization. However, it's a bit more challenging to maintain the epsilon deviation constraint within this Cayley parameterized orthogonal matrix. To tackle this, we employ a mathematical tool known as the Newman series, which helps us simplify our understanding of the Cayley transform. By using this series, we can approximate our R matrix as being very close to I, with a small deviation influenced by the matrix Q. So, if we shift our constraint of epsilon deviation to within the Cayley transform, it's like saying that the difference between our matrix Q and an all-zero matrix, denoted by 0 feet, should be within a certain limit, represented by another error hyperparameter, epsilon prime. This new constraint on the Q matrix can then be enforced using a method called projected gradient descent. To make R start off as the identity matrix, we set Q as an all-zero matrix at the beginning. So, in essence, COFT combines two types of constraints: minimal changes in a spherical energy measurement and a limited deviation from the original pre-trained model. Many existing fine-tuning methods implicitly apply this second constraint. However, we have found that by explicitly incorporating it into our COFT approach, we're able to enhance the stability of the fine-tuning process even more than what is possible with the standard OFT, making it a worthwhile refinement. Section summary. The constrained orthogonal fine-tuning (COFT) method limits the flexibility of the original OFT by constraining the fine-tuned model to be within a small neighborhood of the pre-trained model. COFT uses an orthogonality constraint and an epsilon deviation constraint to an identity matrix, which can be enforced by projected gradient descent. This method yields even better fine-tuning stability than OFT due to the deviation constraint. Section 4. Intriguing insights and discussions. We'd like to share 4 enlightening findings and discussions based on our study. 1. The orthogonal fine-tuning (OFT) technique we developed is universal and can be applied to any type of neural network. For instance, we can use it with transformer models, where a similar method called low-rank adaptation (LoRA) is generally applied to adjust attention weights. To ensure a fair comparison with LoRA, in our studies we've also only used OFT to fine-tune attention weights. However, OFT goes a step further and can also fine-tune fully connected layers and convolution layers. This is due to the block diagonal structure of the orthogonal matrix R, which has meaningful interpretations when applied to convolution layers. If the number of blocks in R is the same as the number of input channels, each block only modifies a unique neuron channel, which is similar to learning depth-wise convolution kernels. If all blocks in R are shared, the OFT modifies neurons using an orthogonal matrix shared across channels. 2. Drawing a connection between OFT and LoRA, both methods aim to prevent drastic shifts in information within the pre-trained weight matrix during fine-tuning. LoRA achieves this by adding a low-rank matrix to the mix, while OFT ensures that the transform applied to the pre-trained weight matrix is orthogonal, effectively maintaining the integrity of the pre-trained information. This can be visualized in OFT's forward pass equation, where a term similar to the low-rank weight update in LoRA is present. OFT also performs low-rank weight updates when the difference between the orthogonal matrix R and the identity matrix I is low rank. Like LoRA, OFT too uses a parameter, in this case, a diagonal block parameter, to reduce the number of trainable parameters. 3. OFT often converges faster in the optimization process. This is due to 2 main reasons. First, the most effective way to alter the semantics is by changing neuron directions, which is precisely what OFT is designed for. Second, OFT's method of fine-tuning neurons can be viewed as a process on a smooth hypersphere manifold, which yields a better optimization landscape. 4. While we do not aim to minimize hyperspherical energy in our study, it's an important distinction to make from other models. Minimizing hyperspherical energy is often beneficial in classification problems where redundancy among neurons is undesirable. But in fine-tuning a pre-trained generative model, such an objective could lead to loss of pre-trained information, which isn't what we want. In our fine-tuning process, we discovered a trade-off between flexibility and regularity. Standard fine-tuning offers great flexibility but often leads to instability and risks model collapse. Our OFT method, in its simple design, strikes a good balance between these 2 aspects. It maintains pairwise neuron angles and brings about regularity and stability in fine-tuning, despite limiting flexibility. Our constrained OFT-COFT method further exemplifies this principle. An added advantage of OFT is that, unlike other models like DreamBooth and ControlNet, it doesn't add any extra computational load during inference. Once the orthogonal matrix R is learned, it can be multiplied with the pre-trained weight matrix to get an equivalent weight matrix for inference. This keeps the inference speed on par with the pre-trained model. Section summary. The orthogonal fine-tuning (OFT) technique can be applied to any type of neural network, including transformers, and is well suited for fine-tuning convolution layers. OFT controls the transform that applies to the pre-trained weight matrix to be orthogonal, preventing it from destroying the pre-trained information. OFT converges faster because it fine-tunes neurons on a smooth hypersphere manifold, which yields a better optimization landscape, and finds a good balance between flexibility and regularity by preserving pairwise neuron angles. Additionally, OFT introduces no additional inference overhead to the fine-tuned model. Section 5. Experiments and results. In our experiments, we used the stable diffusion version 1.5 as our baseline text-to-image diffusion model. The same model was tweaked for each of the compared methods to maintain consistency. The images used for comparison were randomly selected, and our experiment was modeled following the general guidelines of DreamBooth, ControlNet, and T2I adapter. We only applied our techniques OFT and COFT on the same layer where another method called LoRa is used to ensure fair comparison. 5.1 Subject-driven generation. We employed DreamBooth and LoRa as our baselines. All methods utilize the same loss function as DreamBooth. For both DreamBooth and LoRa, we implemented the methods as described in their respective original papers and used the optimal hyperparameters. We assessed the stability and speed of fine-tuning in DreamBooth, LoRa, OFT, and COFT. Our findings revealed that OFT and COFT are highly effective at fine-tuning the diffusion model. After 400 cycles, DreamBooth and OFT could control the output well, while LoRa could not maintain the identity of the subject. Following 2,000 iterations, DreamBooth started to produce distorted images, and LoRa incorrectly generated yellow fur instead of a yellow shirt. However, both OFT and COFT maintained stable and consistent control over the image output, confirming the reliability and speed of our OFT framework in fine-tuning diffusion models. Next, we performed a quantitative comparison to measure subject fidelity, text prompt fidelity, and sample diversity. For this, we used metrics such as DINO, CLIP-I, CLIP-T, and LPIPS. CLIP-I and DINO calculate the average pairwise cosine similarity of the embeddings between the created and actual images. In DINO, we used VIT-S16 DINO embeddings instead of CLIP embeddings. CLIP-T measures the average cosine similarity between the text prompt and the produced images. LPIPS was used to determine the similarity between images generated from the same text prompt and subject. The results showed that OFT and COFT performed considerably better than both DreamBooth and LoRa in the subject fidelity metrics. They also provided slightly improved or similar performance in prompt fidelity and diversity metrics. We fine-tuned each method 30 times with different random seeds to reduce randomness, and found that our OFT framework consistently yielded better final results while maintaining stability and convergence. We also carried out a qualitative comparison to visually demonstrate the advantages of OFT. We generated images using the same fine-tuned model with each method. It was apparent that both OFT and COFT were superior in preserving subject identity, which LoRa often failed to do. Additionally, OFT and COFT provided more precise control using text prompts, which DreamBooth struggled with despite its ability to maintain subject identity. This qualitative comparison affirmed that our OFT framework offers superior controllability and subject preservation. Furthermore, the number of iterations didn't affect the performance of OFT, allowing it to perform well even with a large number of iterations, a feat neither DreamBooth nor LoRa could accomplish. Section summary. The experiments and results section compares various methods for subject-driven and controllable image generation using a pre-trained text-to-image diffusion model. The OFT and COFT methods outperform DreamBooth and LoRa in terms of subject fidelity and control accuracy, while achieving comparable performance in prompt fidelity and diversity metrics. OFT also demonstrates better convergence and stability, and delivers excellent subject preservation and accurate control using text prompts. Section 5.2 Controllable Generation. In Section 5.2, we discuss the process of controllable generation, using models like ControlNet, T2I adapter, and LoRa as a baseline. We tackle 3 challenging tasks, namely, converting canny edges to images, C2I, on the COCO dataset, converting segmentation maps to images, S2I, on the AID20K dataset, and converting landmarks to faces, L2F, on the Celeba HQ dataset. For each task, we fine-tune the stable diffusion, SD, method over 20 cycles. You can find more details and results in the appendix. Next, we analyze the speed of convergence of our models on the L2F task. To do this, we measure and compare the average distance between the controlled face landmarks and predicted face landmarks for each model. Our observations indicate that both COFT and OFT converge at a faster pace compared to other models. In fact, our OFT framework achieved in 8 cycles what LoRa achieved in 20 cycles. Both OFT and COFT are particularly efficient to train and converge faster than existing methods, despite having a similar number of trainable parameters as LoRa and significantly fewer than ControlNet. Further, OFT's faster convergence has been verified with results that show that OFT requires only 5% of the AID20K dataset to converge, proving it's more data efficient than ControlNet and LoRa. For quality comparison, we particularly examine OFT, COFT, and ControlNet, as ControlNet delivers the closest landmark error to ours. We found that OFT and COFT converge steadily, and the face pose gradually aligns with the control landmarks. However, ControlNet's controllability suddenly peaks after 8 cycles, which validates the sudden convergence phenomenon. The stable convergence of our OFT framework makes it more practical to use, given its predictable and continuous learning behavior. For quantitative comparison, we use a consistency metric for controllable generation, which compares the control signal from the generated image with the original control signal. In the C2I task, we use intersection over union, IOU, and F1 score as metrics. For the S2I task, we calculate the mean IOU, mean, and overall accuracy. For the L2F task, we compute the average distance between control landmarks and predicted landmarks. The results indicate that both OFT and COFT are more precise and control-oriented compared to other models. We also qualitatively compare OFT and COFT with ControlNet, T2I adapter, and LoRa. We found that OFT and COFT not only yield higher quality and more realistic images but also demonstrate accurate control. For the S2I task, it's evident that LoRa failed to generate images based on the input segmentation map, while ControlNet, OFT, and COFT were able to accurately control the generated images. Notably, OFT and COFT generated higher quality images with more vivid details and better geometric structures, despite using fewer model parameters than ControlNet. In the C2I task, both OFT and COFT could generate images with similar semantic meaning based on rough canny edges, whereas T2I adapter and LoRa performed poorly. For the L2F task, our method produced the most accurate pose control for generated images. In conclusion, we demonstrate the effectiveness of both OFT and COFT in controllable image generation. Section summary. The authors evaluate the performance of ControlNet, T2I adapter, and LoRa on 3 controllable generation tasks: canny edge to image, segmentation map to image, and landmark to face. They find that OFT and COFT converge faster and are more data efficient than existing methods, while also achieving stronger and more accurate control. Qualitative comparisons show that OFT and COFT generate high-fidelity images with more vivid details and reasonable geometric structures, while producing the most accurate pose control for generated images.